Understanding binary representation in digital systems. Imagine a universe where everything boils down to just two states, on and off, yes and no, or simply 1 and 0. This seemingly simple concept powers every electronic device you use, from smartphones to supercomputers. Today, we will decode the mystery behind binary representation, the language of machines. We use base 10 number system in our everyday life, engineering, commerce, etc. In base 10 number system, there are 10 symbols, 0 to 9. In base 2 or binary system, there are just 2, where every digit is either 0 or 1. But what makes this system so magic? Well, it perfectly aligns with the physical reality of transistors in electronic devices. As we know that a computer consists of billions of transistors. Transistors have two states, on or off. By understanding the binary, we unlock the key to how data and numbers are stored, processed, and transmitted. Let's start with binary representation of numbers. In binary, each position of a digit represents a power of 2. Think of it as a game of exponents. For example, the binary number 1011 means, starting from the most significant bit, 1 into 2 raised to 3 plus 0 into 2 raised to 2 plus 1 into 2 raised to 1 plus 1 into 2 raised to 0. That is equal to 8 plus 0 plus 2 plus 1, equal to 11 in decimal. This is how computers effortlessly handle numbers. But there is more. Numbers in binary can be unsigned or signed. Unsigned binary numbers represent non-negative integers directly using base 2. It's straightforward, no sign, just the magnitude. For example, a 4-bit unsigned binary can represent numbers from 0 to 50. 0 corresponds to 000 and 15 corresponds to 1111. Simple, right? Now, let's add some spice. What if we want to represent both positive and negative numbers? That's where signed binary numbers come into play. Computers have clever ways to do this, such as sign magnitude representation, 1's complement, and the most popular, 2's complement. Let's break them down. First one, sign magnitude representation. The first bit is the sign, 0 for positive and 1 for negative. For example, 1001 in 4-bit means, as the MSB is 1, it is negative number, and balance 001. That corresponds to magnitude 1. 1's complement. Flip all the bits of the positive number to get the negative. Example, plus 1 is 0001. So minus 1 is 1110. 2's complement, the superstar. Take the 1's complement of the number and then add 1. Example, minus 1 in 4-bit is 1111. Invert 0001 and add 1. Why is this favorite? It simplifies arithmetic, making addition and subtraction seamless in digital circuits. What about real numbers like fractions? For that, we use floating point representation, typically following the IEEE 754 standard. In this system, a number is expressed as minus 1 raised to s into m into 2 raised to e, where s is sign bit, 0 means positive, 1 means negative, m the mantissa which holds the significant digits in binary, e the exponent which scales the number. Floating point numbers bring precision to tasks like scientific computing and graphics rendering. The range of numbers we can represent depends on the number of bits. For an n-bit unsigned integer, the range is 0 to 2 raised to n minus 1. For an n-bit signed integer, the range is minus 2 raised to n minus 1 to 2 raised to n minus 1 minus 1. For instance, with 4 bits, unsigned integer numbers range from 0 to 15. Signed numbers range from minus 8 to 7. This flexibility in representation is what makes binary so powerful. In summary, binary representation is not just a way of encoding numbers, it's the lifeline of digital computing. Here's a quick recap. Unsigned binary, pure magnitude, no sign. Sign magnitude, first bit indicates the sign. 1's complement, flip the bits for negative. 2's complement, flip and add 1 for negative. It's the go-to method. This versatility enables everything from arithmetic operations to complex data processing. Truly, binary is the unsung hero behind every computing marvel.